Hello and good day, Algebra. Here with you to go over packet number 10, which is due April 15th, tax day for the adults in your life. So the first question here, you deposit 2/3 of your paycheck to the bank. Smart. You spend half of the remaining amount on an amusement park ticket, then another $15 on a shirt. After all this, you have $7 left. How much money was your paycheck? So with the class that I went over this with, we kind of started at the top here. It said, here's our paycheck, right? 2/3 of this went to the bank, which means that 1/3 of this was left for us to spend. And with that 1/3, we spent half of that on an amusement park ticket, okay? And then another $15 on a shirt. After all this, we have $7 left. So here we spent $15 on a shirt, and that left us with $7 left. And so you think about where you end, and think about how you got there, kind of climbing that tree back to the top of the paycheck. This is probably the most organized or efficient way to do it. I think we also talked about that, with the spending half of it here. If that's not half of the original amount, right? It's not half of the paycheck. It's half of the remaining amount. So half of this third is 1/6. Okay. So if you want to go about it that way, you can use that knowledge too. But I think working backwards here, starting with the end, having $7 left and knowing what you spent things on to get there, allows you to kind of work your way back up to the top. And then when you get your final answer, plug it in here, right? If your check, and this, I don't think this is correct here, but if your check was $200, plug $200 in here and work your way down through the tree, and see if you get an end result of 7. That's a great way to check your answer. So that should get you started on this one. And in fact, that working backwards theme, we're going to continue that in the second one. You are exploring an uncharted section of the rainforest and discover a plant that grows 3 times its size every day, but then shrinks to half its size every night. After 3 days and nights, the plant is 6.75 inches tall. How tall was the plant at the start? Okay, so you know that it ends at 6.75 inches. Okay, and to get there, right, it says after 3 days and nights. So before this, it would have been a night, right? To get to 6.75, it shrinks to half its size. So we're actually going to want to double 6.75, which is 13 and 0.5, to say that the night before, it was 13.5 inches. Because when it shrank to half its size, it ended up at 6.75 inches. Okay, which means, what was it then during the day? Well, it says during the day, it grows to 3 times its size. So during the day, it would have had to have been 4.5 inches tall. So that when it grew 3 times its size, it got to 13.5. Then it shrunk to half its size. It got to 6.75 as the final. Well, if it was 4.5 inches during the day, what was it the night before that? Right? So you can kind of work backwards here and just kind of make sure everything fits together. All right. So that when you're all done, right? Here's night 3. Here's day 3. Here's night 2. We're going to have day 2 here, night 1 here, day 1 here. When you get this value for day 1, you can go through the process. Triples its size, half its size. Triples its size, half its size. Triples its size, half its size. And you should end up with 6.75 inches, as a final answer. So working backwards theme here for both of our logic questions to start out. Then we move on to our 5-card challenge, which we can see you've got an ace, Spirit of Christmas, and you're using those 5 cards to make a 2. Just make sure that you are writing an equation using all 5 cards. Make sure you get the correct number of points. Plugging these things into a calculator is a great way to check your answer, because the calculator always does the correct order of operations. And so if you do make a mistake, if you miss a set of parentheses, then checking with your calculator should help you catch that. Next one, equivalent expressions. How topical that we just finished PO49 and PO50, and here we are at a trinomial which can be factored. So a couple different ways that you can attack this one. You can start with the original trinomial here and factor it and see which set of expressions you get, keeping in mind that, you know, it's possible to be able to factor a trinomial multiple ways. If I give you a number like 60 and say, you know, what are the factors of it, there are several different factor pairs that you can write, you know, and all of these would be correct. I think that's all of them, okay? And so if you factor this and you get one of these, it doesn't mean all the others are wrong, okay? So you might have to look for, well, what are other ways I can place my numbers, rearrange things to get other expressions as well. Another option, if that doesn't sound like very much fun, another option is to take an expression and FOIL, crab claw, or box it to see if you get the original trinomial, and then do that for all of them. Okay, so you can factor the original, see what you get there. You can FOIL, crab claw, box each of the ending expressions to see if you get back to the original. Or, as we've done before, you can pick a value for x, plug it into the original expression, and whatever value that you get, plug that same x into each of our ending expressions, and you should get the same answer as you got with the original if the expressions are equivalent. If you get something else, it means they are not equivalent. Okay, so a couple of different ways to attack this one. You can do which one works best for you, but don't forget to defend your decision. If all you give me is a yes or a no, I can't give you credit. I have to see how you reached that conclusion. Then we come to our percentage of the figure that is shaded. We've got the area of the original figure, which is a square, so that 32 side length given is important. Okay, it's the length of all the sides there. For the shaded region, we've come across situations like this before, where our most efficient plan of action here is to start with the area of the entire figure and subtract the area of the white sections. Because if we subtract the white parts, we're left with the shaded part, right? So the white part here is made up of 16 circles, and the area of a circle is pi times the radius squared. There is enough information here, just knowing the side length of the square, the fact that all these circles are congruent or the same size, means there is enough information to get the diameter and the radius of one circle, because once you find the area of one circle, multiply by 16, you've got the area of all of the circles, which you can then subtract from your total area, and that's going to leave you with the shaded part. Right? So that's kind of your plan of action here. Use that 32 to get the dimension you need, which is the radius of just one circle. Find the area of that, expand it to 16 circles, and then do your subtraction. Then we come to our pattern block section. And similar to the last few packets that we've had, we're dealing with squares, which means this total blocks section, this total blocks column, has a very distinct pattern. If you just kind of look at what we've got going on here, the first figure has 1 total block, the second figure has 9 total blocks, then we get to 25 total blocks, 49 total blocks. Hopefully by now you are recognizing those numbers for what they are, why they're special. They are perfect squares, right? And more than that, they are odd perfect squares. So once you get past figure 5, and you know, unless you draw the figures out, can't count the squares anymore, you can use that pattern to project how many total blocks each figure is going to have. If you know the total, calculating all the 4 colors becomes a much easier task, because like we said in class, you know, only one color changes each figure. In figure 2, we still have 1 yellow. We gain 8 pink because 1 plus 8 equals 9, which is the total, and there are no blue, there are no red. Figure 3, still the 1 yellow, still the 8 pink. We haven't added any red yet, so how many blue are there? Well, if there are 25 total, 9 of them are not blue, yellow and pink. It means that 16 of them are blue. Figure 4. We know there are 49 total, still 1 yellow, 8 pink, 16 blue. Now we're finally adding red. How many red would we have to add to get to our total of 49? Well, 1 plus 8 plus 16 is 25, plus 24 is 49. Figure 5, we're adding yellow again, which means that pink doesn't change, blue doesn't change, red doesn't change. We know the total. What's the missing value there to get a total of 81? And then we can say, oh, there are 33 yellow. 32 yellow added, plus the one we already had, 33 yellow blocks in all. So remembering that only one color changes in each figure and being able to calculate that total with such a distinct pattern makes this a little more manageable than perhaps it first looks. And your job, algebra, is to complete the table all the way down through figure 12. Next up, we have our surface area page, and we're dealing with a triangular prism. First up, you do need to draw a net of the figure, okay, which is if we kind of cut this 3D shape apart and laid it out flat, what's it going to look like? Notice it's got 5 surfaces. You've got 3 rectangles, 2 that kind of make up the slanted sides of it, and then 1 rectangle on the bottom, and then 2 triangles that make up the ends. Okay, and it's important to note that your 2 rectangles that make up the sides, they are a different size than the triangle that makes up the base. Okay, that bottom side. So just keep that in mind when you draw your net and label the sides. Your question here for algebra says the surface area of the 3 rectangles. In class, when we went over this, I wasn't paying close enough attention, and I went with the entire figure, but the surface area of just the 3 rectangles is 540 square inches. What is the volume of the figure? So with that information, you need to be able to solve for the x variable. And remember that surface area is the sum of the areas of the surfaces that we're talking about. So the 3 rectangles here, what are the areas of those 3 rectangles? Okay. Well, we said in class that the one on the side here has dimensions of 10 and x. So the area of that rectangle is represented by 10 times x. And then the rectangle on the back side here, right? This one, well, here, let me do that in a different color. This rectangle here also has dimensions of 10 and x. So it too, its area is represented by 10 times x. And then the last rectangle, the one on the bottom there, I'm going to overlap my greens here. That has dimensions of 12 and x. So its area would be found by multiplying 12 and x together. And since the surface area is the sum of these 3 rectangles' individual areas, we know that 540 is equal to 10 times x plus 10 times x plus 12 times x. We've written an equation. That's the best thing you can do in mathematics to look for relationships. Find an equation. Because what an equation does is it relates something to something else with equality. And if we have an equation, we've got all these different methods that we've talked about to solve for a variable, and you can do that here. And once you get that value for x, right, that represents the width of the prism, and your ultimate question, what is the volume? The formula for volume is base times width times height divided by 2. So that x is crucial. It represents the width of the triangular prism, and with that you can find the volume. But it starts here with this equation here, and also don't forget to draw the net of the figure as well. And that brings us, excuse me, to our magnificent 7. Your job is to complete 4 of these 7 with the given volume. What are possible lengths for the base, the width, and the height, or the radius, or whatever it calls for. You start, your first figure is a rectangular prism. Keep in mind, this second one being a cube here, the base, the width, and the height all have to be the same number. That would multiply to give you 1,331. And just as a point of reference to keep in mind here, let's go to our triangular prism one, the same shape we have in the surface area. The volume formula is base times width times height divided by 2, okay? Which means that the numbers that you choose for the base, the width, and the height actually have to multiply to equal 140. Because when you divide that by 2, that's how you get the final volume of 70. So pay attention to the formula, okay? Because sometimes I'll get papers turned in where the base, the length, the width, and the height multiply to be 70. But since the formula has us dividing that product by 2, okay, we actually have to go for 140. So that when we divide by 2, it'll equal 70. Otherwise, pretty straightforward, similar to the ones you've had in the past. Just make sure you are completing 4 of the 7 and to check your work. Next, we get to bidirectional Fibonacci. We've talked about the Fibonacci sequence in the last couple of packets. We've talked about how it's formed, that each number in the sequence is the sum of the previous 2 numbers before it. So 1 plus 1 is how we get 2. 1 plus 2 is how we get 3. 2 plus 3 is how we get 5. 3 plus 5 is how we get 8. 5 plus 8 is how we get 13. 8 and 13 is 21, and so on and so forth. Okay? Well, I don't know who came along, but someone came along and said, well, does Fibonacci also go left? Right? Like we start with this F1 here, which means the first number in Fibonacci. Is there a 0th number of the Fibonacci sequence? Is there a negative first number of the Fibonacci sequence? Okay, and the answer is actually yes. And this whole section here, normally we would have already kind of covered some of this stuff in general class, but we did not get to this here. And so, kind of jumping down to the end here, we're just going to, I don't know what that shape is. We're just going to kind of look at this logically, knowing what we already know about Fibonacci. To say that, okay, looking at the 0th number in the sequence here, what number would that have to be so that the 0th number plus 1 gives us 1? Which is what the Fibonacci sequence represents, is what we talked about up at the top here. Well, 0, right? 0 plus 1 gives us 1. Okay, so let's continue back here now. Looking at the negative first number. What would that number have to be so that the negative first number plus 0 gives us 1? Well, what number plus 0 equals 1 is essentially what we're looking for here. Well, that's 1. 1 plus 0 equals 1. Okay. Let's go back another one to the left here. F negative 2. What number would that have to be so that when we add 1 to it, we get 0? And if you're looking in kind of like equation terms, we're saying, make this our variable, x plus 1 equals 0 is essentially the equation that we're trying to solve here. Oh, well, negative 1 plus 1 equals 0. Okay. Let's go back another one here. What number plus negative 1 equals 1? Again, x plus negative 1 equals 1. Well, 2 plus negative 1, right? Or 2 minus 1 equals 1. So it turns out you can take Fibonacci back to the left into the negatives here. And as you start to fill this out, I think you're really going to like the pattern that develops here. Another application, another instance where Fibonacci, we've talked about how it appears in music, talked about how it appears in nature. Here it appears in mathematics in interesting ways that you just might not expect. So your job is really to only complete the table here. And I've got you started going to the left there. Keep going back, working backwards all the way to the negative 11th term of Fibonacci. Our probability tree diagram number 2. Here's the situation. The probability that Jane will hit a target, I don't know if they're doing arrows or darts or that's virtually the same thing, but probability that Jane will hit a target is 4/5, which means that every 5 times that she shoots, she's going to hit it 4 out of the 5. The probability that Gary will hit the target, the same target, is 3 out of 4. Every 4 times that Gary shoots at it, he's going to hit it 3 times, 3 out of the 4. And the question is, if each of them fires once, find the probability that the target will be hit by both of them, and then only one of them. Okay. Now, this is a question that if you saw it on a map test, you'd probably say, oh boy, let's see, I'm going to guess option C. It's always C. Click, and you move on, right? Well, the probability tree is a great way to fairly quickly, once you understand what you're trying to do, find the answer to this. And so my goal of putting this in the math packet, since we don't talk about probability much in the general curriculum, is to give you these tools to answer these types of questions when you see them come up. So here's my probability tree here, over on the right side here, right? I'm going to move my little hand icon up there. Okay, so we've got Jane and we've got Gary, right? Here's where we start, and Jane shoots first. There is a 4/5 probability that she hits the target. H stands for hit, which means that there's a 1/5 probability, if you follow the tree down, a 1/5 probability that she misses, which is M. So let's assume that Jane hits it, which is a 4/5 or 4 out of 5 chance of happening, right? Now we're here. Jane hit the target, okay? Now Gary shoots. There's a 3/4 probability that Gary hits the target. And so to find that combination's chances of happening, where they both hit it, you're going to multiply those probabilities together. Actually, I should probably write this over to the left a little bit here. 4/5 probability that Jane hits it, 3/4 probability that Gary hits it, 4/5 times 3/4 is how we get the hit outcome of 12/20. Okay, let's say that Jane hits it, which is a 4/5 probability, but Gary misses it, right? If he misses it, that's a 1/4 chance of happening, because if it's 3/4 that he hits it, the only other option is that he misses it, which would be 1/4. So the combination of hit miss, Jane hits, Gary misses, is 4/5 times 1/4, which is 4/20, the probability that you see there. So now let's say, all right, what if Jane doesn't hit it? What if Jane misses it? There's a 1/5 probability that Jane misses, because if it's 4/5 probability she hits it, 1/5 that she misses. So the combination of miss hit, Jane misses, Gary hits it, is 1/5 times 3/4, right? Because we're saying Jane misses, Gary hits. The probability of each of those, 1/5 times 3/4, multiply those together, and we get the miss-hit combo of 3 out of 20. Well, let's say they're both having off days and they both miss, right? 1/5 probability that Jane misses, 1/5 probability that Gary misses, 1/4 times 1/5, multiply those probabilities together, and it's a 1 in 20 chance that we get the miss combo there. And if you notice, the 4 fractions that we have in our outcomes column, 12/20 plus 4/20 plus 3/20 plus 1/20 add up to equal 20/20. We've covered every possible combination here. So when you're doing your own tree and you get to that outcome column, make sure your fractions all add up to equal one whole. That's how you know you didn't miss anything and that you've multiplied your probabilities correctly. So back to our original question, the probability of hit is 12/20ths, which we see here, and 12 divided by 20 is 60%. The probability only one of them hitting the target, which is the outcomes of hit, miss, or miss, hit, 4/20ths for hit, miss, 3/20ths for miss, hit. We're adding those together to get 7/20ths, right? There are 4 out of 20 ways for them to hit, miss, 3 out of 20 ways or probability for a miss, hit. The sum of those is one of them hitting the target, 7/20ths or 35%. So your job now. A box contains 3 yellow chips and 5 blue ones for a total of 8. 2 chips are drawn at random, one at a time from the box with replacements. You pick up the chip, you put it back. Using a probability tree, calculate the probability that both chips drawn are yellow, and then one chip is yellow and one chip is blue. So like the tree that we had here, we're starting here, okay? We reach in the bag for our first draw number 1. What could we get? Right? We could get yellow, or we could get blue. What's the probability of a yellow? Well, there are 3 yellow chips out of 8, so the probability is 3/8. What's the probability of picking a blue chip? There are 5 out of 8, so 5/8. Okay. Now we draw a second time, and we could either get, again, a yellow or a blue. A yellow is 3/8, a blue is 5/8. If we got a blue one the first time, we could get a yellow or a blue the second time. 3/8 probability for yellow, 5/8 probability for blue. So now on our outcome column, right, what's the probability of getting a yellow? What's the probability of getting a yellow and then a blue? What's the probability of getting a blue and then a yellow? Or a blue and a blue? And like we did up above here, you are going to want to, multiply these probabilities to get that outcome. A yellow is 3/8 times 3/8. You'd fill it in here in your fractions, and again, make sure they all add up to one whole when you're done, and then use that to answer the questions here. Okay, last one, we have our polyominoes. Each of these 10 appears in the figure on the right exactly the way that it appears on the left. There's no flipping, no turning, anything like that. I highly recommend that you do this question in pencil so that if/when you make a mistake and need to fix something, it doesn't get too messy for you. But there you have it. There's math packet number 10. It is due on April 15th. I recommend you turn it in early, especially if it is one of your bingo squares. Happy to answer any questions through email or when you get back from a break. Thanks for watching. Have a great day, and don't forget to like and subscribe.